Hello, in this vodcast we are learning about the atmosphere, and our learning targets for this vodcast are first to know the layers of the atmosphere and the composition of the atmosphere. Our second learning target is to explain how uneven heating causes convection currents in the troposphere, which is the lower layer of the atmosphere. First, the Earth's atmosphere is composed of four layers: the thermosphere, the mesosphere, the stratosphere, and the troposphere. And here is a diagram showing the layers and showing what happens to the temperature. Now you notice that the lowest layer is the troposphere, and you see how the temperature decreases. The tropopause is the very top of the troposphere, and it's called pause because that's where the trend of the temperature pauses, and it stops going down and then it starts going up. And in the stratosphere, temperature goes up, and that's where you find the ozone layer. And then in the stratopause, it pauses, and then it starts going down in the mesosphere. And then the mesopause, it pauses, and that's basically the top layer. So the defining characteristic of each of the layers of the atmosphere are the temperature trends. So to be more specific of the different layers, for the troposphere, it ranges from a depth of 18 kilometers over the equator to 8 kilometers over the poles. And you need to know that that's where all weather occurs in the troposphere. There is no weather in the other layers. And the convection currents in the troposphere redistribute the heat and moisture around the globe. And also that air temperature drops with increasing altitude. And that the tropopause is the transition boundary, and it limits the mixing between the troposphere and the stratosphere. The stratosphere is the next layer. The stratosphere is the next layer up. It has almost no water vapor, which means that you'll find basically no weather in there. You will once in a while find clouds in there when it's very, very cold above the air. But you will find much more ozone in the stratosphere than the troposphere, and that's where you find the ozone layer. And the ozone layer absorbs ultraviolet light that warms the upper part of the stratosphere. And because it's absorbing the ultraviolet light, that's the reason why temperature is increased in the stratosphere. Light is energy, and as it absorbs it, that light energy turns into heat energy. By absorbing all that ultraviolet light, that is what is protecting life on Earth, because the ultraviolet radiation damages living tissues. What that ultraviolet light does to us, at least the parts that reach here, is it can cause skin cancer, it can cause sunburns, it can cause cataracts. Mesosphere is the next layer up. It's the middle layer, and there we don't need to be too concerned with that layer. Thermosphere is pretty much the top layer that we need to be concerned with, and temperature increases there because in that layer it absorbs even more dangerous rays than ultraviolet. It absorbs cosmic rays, it absorbs X-rays, gamma rays. That's where you find the aurora borealis. If these rays were to come through, it could cause blackouts. It could also cause much higher rates of cancer than ultraviolet, because these high energy rays are much more dangerous than ultraviolet. Because these light rays are absorbed, that's turned into heat, and that's why temperature increases in the thermosphere. Now here we have two pie graphs showing it's mostly nitrogen and oxygen. Of the trace gases, it's mostly carbon dioxide. And you see number 3, which is carbon dioxide, it's 0.038%. Now we're up to the next part, which is the uneven heating is going to answer this question here. What direction do storms travel in the United States? If you think about it, they all travel from west to east. We look at what storms are going to hit New York. We don't look out in the Atlantic. We look out in the direction of, say, Ohio. One exception to that was Hurricane Sandy, but that was a very unusual exception. Now with hurricanes, of which Sandy was one, but that was an exception. If you look over here, this was Hurricane Isabella, and here's one place where it is, and this is not an exception. This is a rule for storms in that area. See, this is just 3 days later, and you see it's moved the other direction. But even so, the general track of storms, of hurricanes actually, is at lower latitudes they tend to travel west, and then when they get up to the mid latitudes where we are, they tend to travel east. Why does this happen? Before we get to that, we have to look at what causes this. First of all weather ultimately is caused by the sun. And we'll see why this is as we go on through this podcast. First word we have to know is the word called insolation. Insolation comes from three words: incoming solar radiation. Now, as the incoming solar energy comes through, several things can happen to that light, and that's shown in this diagram. And that's shown in this. Only 45% of that incoming solar radiation gets absorbed by the surface, and that's on average. How much it depends on how bright the surface is. For example, snow reflects practically all of it, while dark soil will absorb practically all of it. The 25% gets absorbed by the atmosphere and clouds, while 25% gets reflected by the atmosphere. Re-radiated, that means that the stuff that gets absorbed doesn't stay absorbed, but it gets re-radiated as heat, and eventually it goes out into outer space. You see down here is the greenhouse effect, and what happens with the greenhouse effect is that there are certain gases called greenhouse gases, like carbon dioxide, like water vapor, like methane, and what they do is they are transparent to light energy, to visible light energy, I mean, but they will absorb infrared energy, heat energy. Because they absorb it, they hold in the heat, they hold in that energy, and they keep the Earth warm. We'll get into more of that and how the effect of the greenhouse effect in keeping the Earth warm, say, overnight, and the effect of too much of a greenhouse effect in climate change. Now, why is the equator warmer than the poles? Let's look at this diagram here. Now, here's the Earth. Now, these lines here show the sun's radiation coming through, the sun's light or sun's photons coming through. And these dark lines that you see on the surface of the Earth, that represents a flat surface on the Earth. You see, if you look here on the equator, if you count up the number of lines here, we've got here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we got 13 lines here coming at the equator. Now up here in the northern latitudes, we have 1, 2, 3, 4 lines. And that's because this is at an angle, so fewer hit it. And that is why at the equator is warmer, because so much more energy is able to hit it when the sun is directly overhead. Like if you were standing over here, the sun would be directly overhead. Here, directly overhead is in this direction here. The sun would be low on the sky at noon. I know that some people think that the reason why it's colder in the winter and warmer in the summer is because the Earth is closer to the sun in the summer and further from the sun in the winter. That actually is not true. We're actually closest to the sun in January and furthest in June. If you think about this, in places like Australia and Argentina, in January it's not winter, it's summer, it's warmer there. The thing which makes it colder in the winter and warmer in the summer is the angle of the sunlight. In the summer, the sun at noon gets very high overhead, and in the winter at noon the sun is still very low in the sky. That's the reason for the temperature differences. In general, the reason why it's warmer at the equator is because the sun gets very high in the sky, and near the poles it doesn't get very high in the sky. So it's colder at the high latitudes and it is warmer at the low latitudes. So what happens to air when it is heated?
Okay, now we're going to find out what changing temperature does to the volume of a gas. So here we have a balloon, and inside a balloon is a fixed amount of gas. First thing I'm going to do is I'm going to put it into some hot water here. You can see its size here, see how it's grown here. Sound was the water sizzling as it hit the hot plate. I'll take this out and just put in the ice water. Same size beaker. And it's shrunk. This here is a hot air balloon, and what I'm going to do is I'm going to heat up the air inside of it. That's going to make the air in there hotter. It'll be less dense, it'll be less air when it's less dense, it's going to rise up. This here is a heat gun. It's not a hair dryer. This will not work with a hair dryer. This will make it hot enough. On 3, let go. 1, 2, 3. Can you feel it tugging up?
Mm-hmm.
On 3, let go. 1, 2, 3.
So you just saw in that demo that air expands when it is heated. So air at the equator will expand and air at the poles will contract. So what will happen to that expanded air at the equator? So you saw in that other demo, that the expanded air will rise up. And the opposite will happen near the poles, that contracted. So here we have it all written down for you, that heated air expands. The reason why it expands is because it becomes less dense and it rises. Cooled air contracts, it becomes more dense and it sinks. And this is basically what you would imagine seeing. This makes a convection current. That at the equator, hot air rises and then it goes up towards the poles and then it sinks at the poles and then it flows back down towards the equator. So you have a convection current and that distributes the heat across. So it's the uneven heating of the Earth that causes a redistribution of the heat, and that ultimately causes the weather. Your warm air rises in warm regions where the pressure is low. Convection, like in the tropics. Air descends in the cold areas where pressure is high, and that's called subsidence. Now there's something else that's happening that will complicate that, and that's called the Coriolis Effect. And let me show you a demo for that. So here you see the Coriolis Effect. And we're seeing this from two different reference points. We're seeing this on the merry-go-round and off the merry-go-round. When we're off the merry-go-round, you see right here, you see how as the children throw the ball to each other, you see here the ball's just going straight. When you're on the merry-go-round, it seems to be curving. And that's the change in the reference point. And another way you see change in the reference point is just look at the background around the merry-go-round and the merry-go-round itself. On the merry-go-round seems to be still, and the background area seems to be moving around it. When you're off the merry-go-round, the background area around it is still, and the merry-go-round spins. So that's the Coriolis effect. When your reference point is such that you're on something that's spinning, an object that's moving in a straight line appears to be curving. And that is important for us because the Earth is spinning. And because the Earth is spinning, we have the Coriolis effect. When something is moving in a straight line, like the wind, it appears to curve. And everything that we saw in the merry-go-round is true with the Earth too. We don't feel or we don't see the Earth. Just like when you saw from the camera that was on the merry-go-round seems to stay still, and everything around the merry-go-round seemed to spin around the merry-go-round. The sun and the stars seem to move around the Earth. But what's happening, in fact, is that the sun and stars are not moving around the Earth, but the Earth is spinning. So this is what it does to the winds. First thing is in the tropics, the winds move up, and then they move towards the poles. But because the Coriolis effect, they start curving. And eventually they curve so much that they end up going straight east or straight west. Once that happens, then they start sinking because they can't move towards the poles anymore. And at the poles, they just sink because it's so cold, and then they move toward, then the cold air moves towards tropics where it's warmer, but they start curving and eventually can't curve anymore, and then they start moving up because the air is warmed up. And the area in between, which is where we are, those get driven by the two convection cells, the north convection cell and south convection cell. Now the part where the air is going up, the air is all being heated, so it becomes less dense. That's a region of low pressure. And the part where it's going down, it's more dense, it's a region of higher pressure. That's also what's driving the winds. Wind is caused by air moving from regions of higher pressure to low air pressure. So these convection currents are caused by releasing latent heat that's caused by water evaporating. That causes air to rise and to cool, and it loses more water vapor as precipitation. And then warm air close to the equator versus the poles also produces pressure differences that cause the weather. And the air near the surface warms, becomes less dense, and that causes the cool air creating the vertical convection currents. And the pressure differences cause the winds. Now we come to our concluding questions. Number 1, in which layer of the atmosphere does weather occur? Number 2, what does the stratosphere protect us from? Number 3, what are the 2 most common gases in the atmosphere? And 4, what ultimately causes weather? That concludes this podcast, and I'll see you in class tomorrow.